This video covers Stat 454, Chapter 3, Section 2, Graphical Solutions to LPs. Even though an LP can have as many decision variables as we want it to have, in order to build intuition about how to solve them, we're going to restrict our study to LPs in 2 variables for now. So I'm going to first focus on this LP, maximize z equals 3x1 plus 2x2, subject to these constraints: 2x1 plus x2 less than or equal to 100, x1 plus x2 less than or equal to 80, x1 less than or equal to 40, and then our sign constraints x1, x2 bigger than or equal to 0. We're going to graph these linear inequalities, use that graph to determine the feasible region, and then see if a graph of the objective function can help us draw some conclusions about what the solution to an LP should be. In order to graph these constraints, I'm going to do a transformation. Instead of thinking about them as linear inequalities, I'm going to think about them as linear equalities. So x1 and x2 and an equal sign equals 80, x1 equals 40. The reason why I'm choosing to do this is we have a lot of practice from algebra learning how to graph linear equations. I'm going to do this by solving for what I'm going to pair up as the y coordinate. I'm going to denote x2 as the vertical coordinate and solve for x2. That yields these equations. I'm now going to draw my x1, x2 axis. It's not necessary for all of these graphs to be perfect when you create graphs on your own. What you should focus on is, are all of the pieces of the lines correct relative to each other? So I'm going to start by graphing the first one. I notice the presence of the y-intercept of 100. So I'm going to label a y-intercept of 100. And I notice a slope of -2. Using that slope, I'm going to draw a line going down this way. Since I have this one point, I'm also going to plot the x-intercept. That's what happens when x2 equals 0. I get a solution of 50. I'm going to repeat this process for the second equation. 80 is below 100, and a slope of -1 is less steep than a slope of -2. So I'm going to end up with a piece that looks like this at 40. Now, what I see is an intersection point between these 2 lines. I am going to find this intersection point by solving a system of equations. Solve let's see, the first one is 2x1 plus x2 equals 100. The second one is x1 plus x2 equals 80. I am going to use the process of elimination in solving linear equations. I observe that the x2 pieces have the same coefficient. So if I subtract the 2 equations, I get 2 minus 1x1 to be a single x1. I get x2 minus x2 to cancel out, and I get x1 equals 20. Now I need to find the corresponding value of x2. 20 plus x2 gives me 80. This is the substitution step, giving me x2 equals 60. This is the intersection right there. So that happens when x2 equals 20. When x1 equals 20 and x2 equals 60. And then finally, I know I need to plot x1 equals 40. Remember that when you have x equals 40, the input equals a constant. This is a vertical line. So I'm going to make sure that I draw that vertical line right there. And I know this picture is crowded, but I'm just using it to create an initial look. I'm going to take this picture and redraw all of the important parts over here. Let's see. Now that I have all of these pieces drawn, I am going to use the inequalities to figure out which part of this graph is relevant to the LP and which part of the graph is not relevant to the LP. And I'm going to do that through some cross shading. So these horizontal lines are going to satisfy the first LP, the less than LP. These vertical lines are going to satisfy the second LP. And then finally, I know I need everything to the left less than 40. So what I'm interested in is the region that satisfies all of these constraints. Here, here, upwards, diagonal up to this corner, and diagonal right there. It's the region that's shaped like this. This oddly shaped pentagon. That region is the feasible region. Next, we need to figure out how the objective function applies to the feasible region. This is going to be done using the technique of things called isoclines. Iso for same. We have an objective function that looks like z equals 3x1 plus 2x2. While we don't know what the maximum value of z is, maybe we can take a guess. I'm going to say 100 is my guess for an initial z. I'm not sure if this is the maximum value. It's an attempt I'm going to make. So why am I using this? Why am I making this attempt? Because now this is a particular line that I can plot. So going back, if I actually plot it, let me find my image. Plotting the isocline yields a line that looks something like this. On my main figure, it would be visualized somewhere around here. Now that's for a particular isocline for z equals 100. And a very interesting thing happens as you start increasing z. These line segments, as you start plotting them, start rising. You have parallel line segments that rise up through the picture. And as you visualize the shape, see if you can imagine the highest line segment that you can get while still staying in the feasible region. And I think you'll see it's this line segment that's parallel to them all and only happens to touch at this particular corner. This was the corner that we had previously labeled 20, 60. So plugging in 20 and 60 into the objective function yields a maximum value of 180 for this LP. This maximum value arises because when we started drawing lines associated to the objective function, that happened to be the highest line, the tallest line, that still managed to stay feasible. This was obviously a maximize function, a small variation. If you're doing a minimize function, you should lower the values of z instead of raise, and find the lowest corner, that is, find the lowest line segment that is still touching the graph. If you take a look at this figure that I drew, you might use it to start drawing a natural conclusion about the types of solutions that occur from LPs. You probably successfully observed that the line segment happened to touch this LP at what is called a corner point. There is a fundamental theorem of linear programming that says any LP that has an optimal value has a corner point as a solution. This is a powerful theorem because it turns the place we have to look for maximum solutions in from the entire feasible region, from the whole feasible region, the whole thing, infinitely many points, into a list of 1, 2, 3, 4, 5 potential points. This theorem very successfully narrows the field of potential candidates for solutions. So how does this theorem get used in practice? In a few lessons, we will learn the simplex method, which is a method of going through all of the corner points of an LP and trying to find the one that causes a maximum or minimum value. There's a homework associated to Chapter 3, Homework 3.2, number 2. And that ends discussion for Chapter 3, Section 2.